Welcome back. Now that we have understood isomerism, let's try to answer exam practice questions on specific rotation under this same topic, isomerism. Okay, so the question we've been given is this one. This is an exam question, and the topic was optical isomerism, specific rotation. So the question was, a student prepared a solution by dissolving 3.0 grams of an optically active compound in enough solvent to make 100 ml of solution. When the solution was placed in a 2.0 decimeter perimeter tube, the observed rotation was positive 12.6 degrees. The question was to calculate the specific rotation of the compound, and it had 6 marks. Then state whether the compound is dextrorotatory or levorotatory. Then the third question was briefly explain the importance of specific rotation in the study of optical isomerism. And the total number of marks was 10 marks allocated to this question. Alright, so let's get into it. So the first thing we're going to do here is to write the formula. So even before we can do that, let's collect the data. Okay, so the data so the solutions are here. Let's start by collecting the data. So what we've been given, so let's start with so we've been given the mass. So the mass was 3.0 grams. Then we've also been given the volume. So the volume was 100 mils. We've also been given the we've also been given the length, which is 2.0 decimeter. Then we've also been given the observed rotation, which is 12. So the observed rotation is equal to 12.6 plus 12.6 degrees. Okay, so this is the data we have. So whenever you've been asked to calculate the specific rotation, the formula is specific rotation is equal to the observed rotation over concentration multiplied by the length. Okay, and one thing we need to understand here is that the specific rotation and the observed rotation must be in degrees. Okay, so the units must be in degrees. Then the concentration must be always in grams per moles. So grams per moles. Then the length must always be in decimeter. So this is important for us to understand. So as we can see here, we don't have the concentration, but we can calculate from the parameters which have been given. So since it is in grams per moles, we're going to divide the mass by the volume to calculate the concentration. So let's calculate the concentration. So our concentration will be equal to mass over volume, and this will be equal to 3.0 grams over the volume, which is 100 mils. So our concentration will be equal to, if we divide 3 divided by 100 mils, it's giving 0.03 grams per mil. So now we have the concentration. Let me write it this side. Concentration is equal to 0. So concentration is equal to 0.03 grams per mil. Okay, now let's substitute these values in this formula. So our specific rotation will be equal to the observed rotation, it is plus 12.6 degrees, over the concentration we found, it's 0.03. The concentration is 0.03 grams 0.03 grams. Okay, let me just, so it's 0.03. Okay. Let me write it here. Okay, so specific rotation, right? Alright, so our specific rotation will be equal to, our observed rotation we're given was 12.1 degrees plus 12.1, or 12.6, sorry. 12.6 degrees. The concentration we just found to be 0.03 grams per mils. Then the length we've been given it's 2.0 decimeters. So our specific rotation will be equal to, if I punch this, 12.6 divided by 0.03 times 2. So it's given to 10, which is positive. So plus 210 degrees. So that's the solution for the first part. Then the second part states whether the compound is dextrorotatory or levorotatory. For this one, because we are finding the positive specific rotation, it is for that reason, since it is giving the positive value. So this is how we're going to answer it. So let me just write it here. Okay, so our part B, we're just going to say, because we're having a positive specific rotatory, it means that it will rotate the plane parallelized right to the right. Plane parallelized right to the right. So it's saying state whether the compound is dextro. Thus, it is dextro rotatory. So dextro just means D. It's a D compound, so it's dextro rotatory. So it will turn the parallelized right towards the right because the specific rotation is positive. Okay. Then let's answer the third part. Briefly explain the importance of the specific rotation in the study of optical isomerization. Okay, so this one, you can even write it here. Okay, so here are the reasons. So I'm going to say part C. Okay, see. So the importance, number one, this is showing the importance. Okay, so it is used. One of the importance is that it is used to identify and distinguish optically active compound. Used to identify and distinguish optically active compound. This is one reason why specific rotation in the study of optical isomerization is important, because it is used in the process of identifying and distinguishing which substances are optically active or which one are not optically active. If the substance is able to turn parallelized right, either to the right or left we call it is latero. Okay, it is laboratory. So if it is turning in parallelized right to the left, we call it laboratory. If it is turning parallelized right to the right, we call it dextrorotatory. Okay, so the other reason is that it is used to determine the purity and the concentration of chiral compounds. So used to determine the purity of a substance. Then the other reason is that this is also used to compare the optical activity of different enantiomers under standard conditions. Okay, used to compare optical activity of optically active of different compounds. So it's used to compare the optical activity of different compounds to identify and distinguish optically active compound, and also used to determine the purity of the compound. So of the substance rather. So this is where we end. Don't forget to like, share, and also subscribe. Thank you.